everyone, this is Kalpana here. In this video, we are going to solve the given differential equation which is non-exact. So let's get going. Problem. Solve y power 4 plus 2y into dx plus xy cube plus 2y power 4 minus 4x into dy equals to 0. Solution. Given differential equation. Y power 4 plus 2y into dx plus xy cube plus 2y power 4 minus 4x into dy equals to 0. Consider the given equation as equation number 1, which is in Mdx plus Ndy equals to 0 form, which is in Mdx plus Ndy equals to 0 form. By comparing these two, coefficient of differential dx is your m and coefficient of differential dy is your n, where m equals to y power 4 plus 2y and n equals to xy cube plus 2y power 4 minus 4x. If the partial derivative of m with respect to y is equals to partial derivative of n with respect to x, then we can say that the given differential equation is an exact equation. So now let's find the partial derivatives. This is your m and this is your n. Partial derivative of m with respect to y is equals to dou by dou y of for m, y power 4 plus 2y is equals to, since we are doing partial derivative with respect to y, here we don't have any x terms, right? But if we are doing partial derivative with respect to y, x will be treated as constant, okay? Partial derivative of first term with respect to y plus partial derivative of second term with respect to y is equals to partial derivative of y power 4 with respect to y is 4y cube plus here 2 is constant, so you can write this as 2 into partial derivative of y with respect to y is equals to 4y cube plus 2 times partial derivative of y with respect to y is 1 equals to 4y cube plus 2. Therefore, partial derivative of m with respect to y equals to 4y cube plus 2. Now let's find the partial derivative of n with respect to x. Partial derivative of n with respect to x equals to dou by dou x of for n xy cube plus 2y power 4 minus 4x. Since we are doing partial derivative with respect to x, so y will be treated as constant. Is equals to partial derivative of first term with respect to x plus partial derivative of second term with respect to x minus partial derivative of third term with respect to x is equals to constant into partial derivative of x with respect to x plus, both are constant, right? Partial derivative of constant with respect to x is 0 minus constant into partial derivative of x with respect to x is equals to y cube into partial derivative of x with respect to x is 1 minus 4 times partial derivative of x with respect to x is 1, which is equals to y cube minus 4. Therefore, partial derivative of n with respect to x is equals to y cube minus 4. So it's clear that, therefore, partial derivative of m with respect to y is not equals to partial derivative of n with respect to x. From this we can say that equation 1 is non-exact. Since the equation is non-exact, we have to reduce the given equation to an exact equation using integrating factor. Okay, fine. Since the given equation is non-exact and it is non-homogeneous, you can find or you can write the given equation in this form. If this function is non-homogeneous, you can find or you can check whether the function is homogeneous or not using f of kx ky equals to f of x. If f of kx ky equals to f of xy, then we can say that this function is homogeneous. Then the differential equation involving homogeneous function will be a homogeneous equation. Okay, or simply by looking at the powers, you can say whether the given equation is homogeneous or not. Okay, so the power of first term 4. Here you're having 1. Here 1 plus 3 4 4 1. You're having 4 1 4 4 1. So all the powers are not equal, not same otherwise. Since the powers are not same, from this we can say that the given equation is non-homogeneous. If you have equal powers, then we can say that it is homogeneous. Okay, you can check using this. So the given equation is non-homogeneous and also it is not in y into some function of xy into dx plus x into some function of xy into dy equals to 0 form, right? So look at m and partial derivatives. You're having m equals to y power 4 plus 2y. You can take y common from these two terms, right? Y times y cube plus 2. So you can notice y cube appearing in all these three. So we can try 1 by m times partial derivative of n with respect to x minus partial derivative of m with respect to y. Okay, so that y cube gets cancelled. Y cube may get cancelled. Okay, let's see. 1 by for m equals to y times y cube plus 2 into partial derivative of n with respect to x is y cube minus 4 minus of partial derivative of m with respect to y 4y cube plus 2 is equals to 1 by y times y cube plus 2 into y cube minus 4 minus 4y cube minus into plus minus 2 is equals to 1 by y times y cube plus 2 into minus 4y cube plus y cube is minus 3y cube minus 4 minus 2 is minus 6. Now we can take minus 3 common from these two terms, right? This equals to 1 by y times y cube plus 2 into take minus 3 common from these two terms, then you'll get minus 3 times y cube plus 2 minus 3 into y cube is minus 3y cube minus into minus minus into plus minus 3 2s are 6, right? The same thing. You'll get the same thing. Right. This equals to 1 into minus 3 into y cube plus 2 is minus 3 y cube plus 2 by y times y cube plus 2. So here y cube plus 2 gets cancelled. This is equals to minus 3 by y. We don't have any x here, right? It does not involve any x, so we call it as function of y alone. And you can name it as g of y, that is function of y. Okay? Therefore, 1 by m times partial derivative of n with respect to x minus partial derivative of m with respect to y equals to minus 3 by y, which is function of y. So our integrating factor will be e power integral function of y into dy. Okay. What happens if you get a real number instead of g of y? If you get any real number, say k, then our integrating factor will be e power integral k into dy. Okay. Is equals to e power integral for g of x minus 3 by y into dy is equals to e power minus 3 integral 1 by y dy equals to e power minus 3 into integral 1 by y dy is log mod y, which is equals to e power minus 3 log y. We know that m log n can be written as log n power m is equals to e power log y power minus 3, and we know that since e power log some function of y equals to function of y, then this equals to function of y. We know that y power minus n equals to 1 by y power n. Then you can write y power minus 3 as 1 by y cube. So here 1 by y cube is our integrating factor. Right? Now, we can reduce the given equation to an exact equation by multiplying it with this integrating factor. 1 by y cube times the given equation. Consider as equation 2. You can write the above as y power 4 plus 2y into dx plus xy cube plus 2y power 4 minus 4x into dy by y cube equals to 0. Then, if you consider LHS part, you're having two terms in the numerator and one term in the denominator, so we can split this into two terms. Then, y power 4 plus 2y by y cube into dx plus xy cube plus 2y power 4 minus 4x by y cube into dy equals to 0. Then, here you are having two terms in the numerator and one term in the denominator, so we can split this into two terms. Y power 4 by y cube plus 2y by y cube into dx plus. Here you are having three terms in the numerator and one term in the denominator, so we can split this into three terms. Xy cube by y cube plus 2y power 4 by y cube minus 4x by y cube into dy equals to 0. Then 3y's gets cancelled, you'll get y, plus 1y gets cancelled, then you'll get 2y, y square into dx, plus y cube gets cancelled, x plus 3y's gets cancelled here, you get 2y minus 4x by y cube into dy equals to 0, which is in m1 dx plus n1 dy equals to 0 form. By comparing these two, we'll get m1 and n1. Where m1 equals to y plus 2 by y cube, y square, and n1 equals to x plus 2y minus 4x by y cube. If the partial derivative of m1 with respect to y is equals to partial derivative of n1 with respect to x, then we can say that equation 2 is exact. That is, the equation obtained by multiplying the given equation with integrating factor is exact. So now let's find the partial derivatives. Firstly, partial derivative of m1 with respect to y. Partial derivative of y plus 2y y square is equals to partial derivative of first term with respect to y plus partial derivative of second term with respect to y is equals to partial derivative of y with respect to y is 1 plus here 2 is constant here, so you can write this as 2 into partial derivative of 1 by y square with respect to y is equals to 1 plus 2 into partial derivative of, we know that 1 by y power n equals to y power minus n, so you can write 1 by y square as y power minus 2 is equals to 1 plus 2 into partial derivative of y power minus 2 with respect to y is minus 2 into y power minus 2 minus 1 is equals to 1 plus into minus, minus 2 2s are 4, y power minus 2 minus 1 is minus 3. Which is equals to 1 minus 4. We can write y power minus 3 as 1 by y cube, since y power minus n equals to 1 by y power n. Okay, then we get 1 by y cube. This is equals to 1 minus 4 by y cube. Therefore, partial derivative of m1 with respect to y equals to 1 minus 4 by y cube. Now, let's find the partial derivative of n1 with respect to x. Partial derivative of n1 with respect to x equals to dou by dou y of, dou by dou x of, for n1 x plus 2y minus 4x by y cube. Since we are doing partial derivative with respect to x, so y will be treated as constant. This equals to partial derivative of first term with respect to x plus partial derivative of second term with respect to x minus partial derivative of third term with respect to x. This equals to partial derivative of x with respect to x is 1 plus partial derivative of a constant with respect to x is 0 minus, here 4 by y cube is constant, so you can write this as minus constant into partial derivative of x with respect to x. Okay, is equals to 1 minus 4 by y cube into partial derivative of x with respect to x is 1, which is equals to 1 minus 4 by y cube. Therefore, partial derivative of n1 with respect to x is 1 minus 4 by y cube. So from this we can say that the partial derivative of m1 with respect to y is equals to partial derivative of n1 with respect to x. Therefore, dou m1 by dou y equals to dou n1 by dou x equals to 1 minus 4 by y cube. From this we can say that equation 2, that is equation obtained by multiplying the given equation with integrating factor, is exact. Now we need to find the general solution to the given equation. So the general solution of equation 2 will be the general solution of equation 1. We know that the general solution of an exact equation which is in m1 dx plus n1 dy equals to 0 is given by integral over x m1 dx plus integral of terms of n1 free from x into dy equals to c. Now consider the first integral, integral over x m1 dx. Here we will be integrating m1 with respect to x, treating y as constant. This is equals to integral of for m1 y plus 2y y square into dx. This is equals to integral y dx plus integral 2y y square into dx. Let's write the constants outside the integral. Here y and 2y y square are constants, so you can write it as constant integral dx plus constant integral dx. This is equals to y. Integral dx is x plus 2y y square into integral dx is x, which is equals to xy plus 2xy y square. Therefore, integral over x m1 dx is xy plus 2xy y square. Now consider the second integral. Integral of terms of n1 free from x. Integral of terms of n1 free from x into dy. This is your n1, so the term which does not involve x is 2y. This is equals to integral of terms of n1 free from x is 2y into dy equals to 2 integral y dy equals 2 into y square by 2. 2 gets cancelled and you'll get y square. Now, the general solution of given equation is result obtained from the first integral xy plus 2xy y square plus result obtained from the second integral y square equals to c. Or take x common from these two terms, then you'll get x times y plus 2y y square plus y square equals to c, which is the required general solution. Fine. So we have seen a problem from a non-exact equation in this video. Hope you'll understand. We'll see you in the next video. Until then, bye bye.